This video is about the diagnostic tests. Diagnostic tests, statistically, are measures of the performance of a binary classification test. What does this tell us? It measures the performance or the accuracy of a test in which the outcome is binary, meaning two possible outcomes. Let's say, does a particular patient really have the disease or not? So two possible outcomes only. Clinically, this is the ability of the test to correctly identify those patients with the disease. Example are the rapid test kits. Let's say an HIV rapid test kit. How accurate is that rapid test kit in identifying whether the patient really is infected with HIV? Same goes for a COVID-19 rapid test kit. How good is the rapid test kit in identifying those patients who are really infected with coronavirus and not? Another example is not with diagnosis of a disease. Let's say, in identifying whether a woman is really pregnant or not. How accurate is the pregnancy test kit in identifying whether a woman really is pregnant or not? So given a 2x2 table below, suppose you're asked to find the following. What is the probability that the test is positive given that the disease is present? Remember that in probability, the probability of A given B is the probability of A intersection B over the probability of B. So in this case, the probability that the test is positive given that the disease is present is probability that the test is positive and the disease is present all over the probability that the disease is present. So this part here, test is positive and the disease is present, that refers to this value. So that's 2 over the total, which is 16. Over the probability of having a disease, that is 5. There are 5 people here who have the disease, so that's 5 over 16. So that is 2 over 5. In other words, out of the 5 patients with the disease, only 2 were diagnosed by the test. Or in other words, 40% of those with the disease were correctly identified by the test. Let's have another one. Probability that the test result is negative given that the disease is absent. The numerator will be how many have the test result which is negative and at the same time not having a disease. So that is 6 over the total 16. All over the probability of not having a disease, we have here 11 people who do not have the disease, so that's 11 over 16. So this indicates that out of the 11 patients without the disease, 6 were diagnosed by the test. Or in other words, out of those people without the disease, 54.5% were correctly identified by the test. Let's have another example. Disease is present given that the test result is positive. So the numerator here will be 2 out of 16. And the denominator here will be 7 out of 16. So that is 2 out of 7. That tells us that out of 7 patients diagnosed to be positive, 2 of them actually have the disease. meaning out of those patients which are diagnosed to be positive, 28.6% actually of them really have the disease. How about the probability of a disease which is absent when the test result is negative? So the numerator here will be 6 out of 16, and the denominator is 9 out of 16. So that is 6 over 9. In general, if you have a 2 by 2 table with these values, let's say A, B, C, and D, how are you going to get the probability of a test which is positive given that the disease is present? So expanding this conditional probability, again, we have this. The numerator here will just be this divided by the total. And the denominator here will just be this one divided by the total. So canceling this 2, we have A over A plus B. We may multiply that to 100%. That is called as the sensitivity of the test. It's the ability of the test to correctly diagnose who are really having the disease. Or in other words, it's the accuracy of the test in giving out positive results. On the other hand, it's the probability of a test which is negative given that the disease is absent. So by conditional probability, it will be like this. So the numerator here will be this one. So that's D over the total. And the denominator here will be C plus D over the total. So we may cancel this out, so we'll have D over C plus D. We may multiply that to 100%. This is called as the specificity of the test. It's the ability of the test to correctly identify those who really do not have the disease. In other words, it's the accuracy of the test in giving out negative results. How about the probability of a disease is present when the test result is positive? So the numerator here will be A over the total. And the denominator here will be this one, A plus C over the total. So canceling this 2, we have A over A plus C. Again, we may multiply that to 100%. That is called as the positive predictive value. It's the ability of the test in detecting presence of a disease when the test result is positive. Last is the probability of having no disease when the test result is negative. So this part here is just this one, D over the total. And this part here is B plus D over the total. So we may cancel this and we have D over B plus D times 100%. And that is called as the negative predictive value, which is the ability of the test in detecting absence of the disease when the test result is negative. Now, keep in mind here that A here is the number of true positive, B is the number of false negative, C is the number of false positive, and D is the number of true negative. So since A is the number of true positive, then dividing it with A plus B, we have the true positive rate. On the other hand, since D is the number of true negative, dividing it with this total will give us the true negative rate, which is the specificity. Now C here is the number of false positive, and dividing it with C plus D will give us the false positive rate. And since D over C plus D is the specificity, D over C plus D is the specificity, then subtracting it from 1 will give us C over C plus D. Meaning, C over C plus D is 1 minus specificity. On the other hand, since B is the number of false negative, then dividing it with A plus B will have the false negative rate. So since A over A plus B is the sensitivity, subtracting it from 1 will give us B over A plus B. So 1 minus sensitivity will give us this one. So this is 1 minus sensitivity. Let's have an example. Detection of hepatitis C virus RNA in serum by polymerase chain reaction, or called as the PCR assay, is the gold standard for the diagnosis of HCV infection. Suppose that a rapid test kit known as HEPA-C is a test kit known for qualitative detection antibodies to HCV. The 2x2 table below shows the result of 100 rapid HEPA-C test kits. So notice here that instead of disease as present or absent, it is replaced by the result of the PCR screening, meaning this is the result of the gold standard. Okay, whatever is the result of the gold standard, that is the whether a patient really has the disease or not. So compute for the sensitivity, specificity, positive predictive value, and the negative predictive value. So I hope you get these results. So sensitivity is computed here as 38 over 40. Specificity is computed as 57 over 60. Positive predictive value is computed as 38 over 41. And negative predictive value is computed as 57 over 59. You may actually go to a website which is medcalc.org/diagnostic_test.php. All you have to do is to put the 4 values on those cells and click test, and you will have the same results. So this is the sensitivity, this is the specificity, this is the positive predictive value, and this is the negative predictive value. Keep in mind that we want sensitivity, specificity, positive predictive value, and negative predictive value to be high since these are measures of the performance of a test. Now notice here that there are other measures like the accuracy. Accuracy is simply the number of correct test results. So if a patient has the disease, then it must be positive. If a patient does not have the disease, then it must be negative. So that's A plus D over the total. So that's A plus D over the total. Accuracy is simply the rate of the correct diagnosis. Now, why is disease prevalence present in this result? Okay? Why is there a need for prevalence? Let's take a look at these scenarios. Suppose that a rapid test kit is found to have a sensitivity of 99% and specificity of 99%. Is there a reason now to be happy? Hey, we already have a test kit that's 99% accurate. Or should this have more verification? Hey, don't be so excited. The sensitivity and specificity are quite high, and that's good. But I want to know how prevalent is this disease. Let's have 2 scenarios here. Suppose let's have a population of 10,000. And let's say the prevalence is 1%. Meaning, if the population is 10,000 and the prevalence is 1%, that indicates that those who have the disease is just 100. Okay? Now, since the sensitivity is 99%, then we know that the number of positive test results here must be 99. On the other hand, since there are only 100 who have the disease, then we are sure that there are 9,900 who do not have the disease. If the specificity is 99%, then the number of negative test results here must be 9,801. So given that, we now have a total. So let's try now to compute for what we call the positive predictive value. So positive predictive value will just be 99 divided by this total here. And that gives us a 50% positive predictive value, which is kind of a low positive predictive value. If this is the positive predictive value of the rapid test kit, then it will just be useless. Now, let's consider now a population with a prevalence of 10%. Now, since this is 10,000, so that shows that 1,000 actually have the disease. Since the sensitivity is 99%, then 990 of these patients who have the disease is correctly identified. Now, since there are 1,000 cases, we know that this will be 9,000. And since the specificity is 99%, then the value here will be 8,910. And we may compute for the total. Now, computing for the positive predictive value will give us this value divided by this value. And that gives us 91.7%. And that's a relatively good positive predictive value. So if that is the positive predictive value of a rapid test kit, then it may be considered already a good or a quality rapid test kit. So this shows that for a test to have a higher predictive value, the disease must be more prevalent. But of course, we would not want a disease with high prevalence. But at least, there must be sufficient number of cases of the disease so that the positive predictive value will be considerably high. And eventually, we would claim that we have finally found a good rapid test kit. So, in other words, a rapid test kit is not just basically based on sensitivity and specificity. We still have to consider the prevalence of a disease for us to consider the positive predictive value.